All right. Today we will finally talk about matrix multiplication. We've been writing vectors, matrices, but we never tried to actually do any operation with them. Today we will learn the standard definition for matrix multiplication, how it is connected to the linear system of equation, and towards the end of the lecture, we will also talk about permutation matrices and the concept of permutation, how to swap rows using matrices. We know how to do it by hand. Obviously, we can write one line, and we could write that line to be first, second, or third. When you look at it, we don't have any problem recognizing that. But the goal is we have a systematic way to have it on the computer, and we can use our matrix multiplication to do that operation. So for that, we need to talk about partitioning matrices into rows and columns. That will help us to visualize the matrix multiplication operation when we see two matrices. So by the end of this lecture, you should be able to multiply a row vector by a column vector. And when you see a matrix, you can also visualize how you will go about partitioning that matrix in rows and columns. We will also learn a standard definition for multiplication, which I'm using this dot here. That dot means that's the operator, multiplication. It could be any other symbol. That's up to you, what symbol do you want to use. But it's very common to use dot. And then after some point, we also drop dot. We don't even write it because it's understood A and B are matrices. You know, if you want to do something with them, we have to do matrix multiplication. So very important factor in multiplying matrices is that we pay attention to what is the size of each matrix. So by the end of this lecture, you will be conscious about that when you want to do matrix multiplication. And we will go through some examples, and at the end we talk about permutation matrices. Suppose we have a row vector A. I'm writing on top of a row to just make it easier. You don't have to write it. You can just say A. So A row, for now we use visual aids to know that we are talking about a row vector. It's just a vector that all its entries are arranged in a row next to each other. So it has one row, and here, k columns. A column vector, such as B, has k rows and one column. So we talked about this before. Now what we want to do, we want to multiply a row vector by a column vector. And we need to give that a meaning because it's not clear how to do it. So the standard definition in linear algebra is that a product of a row vector by a column vector is this fancy notation that you see here. If you're not familiar with it, I'm going to explain it. It is this, that's how we read it. It's the summation from I to k of multiplying each of the corresponding entries. So what you see here, it's simply saying that multiply the corresponding entries A1 times B1. Now A1 is a scalar. We know how to multiply two numbers. So there's no ambiguity in this part. Plus B2, A2 times B2. We talked about dot, 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 means all the way up to the last element, AK times BK. So sigma means summation. When you write I equals 1, that means it starts from 1. And on top of it, we write K. Of course, you can change it to anything. It can be 10, it can be N. Whatever is the end of that summation. So I is from 1 to K. Now, I is called the dummy index. This is called I hope that's a okay terminology. That's how I learned it. It's called dummy index. It's the same thing in integration later in calculus you might learn. Dummy because it's not real. We're just using it to track as we change the numbers from 1, 2, 3, 4. And once the summation is done, you will not see I. There will be no I. So I is actually here 1, 2, 3, 4, all the way to K, okay? So when you read this, you read it sum over I from 1 to K for A times B, for whatever is the inside of that summation. And we talked about column equality sign means we are defining this multiplication. That's the definition. Okay, is everybody comfortable with the notation and the product of a vector and a column? It is perfectly fine if you find it strange. If it's the first time, just ask. I will explain the notations. Which later in Julia you will see that you can implement this sum using a for loop, for example. For I equals 1 to K, just do something in a loop. Yeah.
So is this basically like a vector dot product?
The question is this basically a vector dot product?
Or similar to it?
It's similar to it. Yes, it is, but dot product is, unlike what you imagine, is a very advanced topic. So we have to define a metric, and that's the a dot product operation for a space that contains all the vectors. That's a topic that we will cover in vector spaces lecture. Halfway through the course, that's when it gets a little heavier. We're going to talk about vector spaces, then we can talk about dot products. But it will be similar to this, right? And there's no shortage of geometric meaning here, but we won't talk about it now because we want to talk about matrix multiplication. All right. Let's see how this works. I have a row vector A contains 2, minus 3, minus 1, 11. And clearly, we have K equals 4. And we have B, another column vector. We have 3, 5, minus 1, minus 2. And we want to do multiplications. Now, first of all, one question. Nobody asked that why we have the same number of elements. Couldn't we define it in another way? Can A be n vector, B be an m vector? Can I multiply them? No, everybody's shaking head that to the left and right that you can't do that. You're very disturbed by the fact that I'm attempting to do that. Whether you know it before or intuitively you're guessing that it doesn't work, the definition will break down. And you're right, because, well, by definition, I am operating over corresponding indices here. They must be A1 and B1, A2, B2, and then when there is A, let's say 10, and B has only 9 elements, there is nothing to multiply. So it is not defined, right? So by definition, the syntax is only correct if we have the same number of entries.
Is matrix multiplication commutative? So could I multiply the column by the vector instead, by the row instead? And would it get the same thing?
A super advanced question. Is matrix multiplication commutative? I'll talk about it when we have an example. It's a very, very important topic. It is not, but we'll see why it's not. But this is the reason later we define what would be the size constraints on matrix multiplication. Because for multiplying a vector by a column, a row vector by a column vector, we must have the same number of elements in each of them. So just tell me how to multiply A times B. You tell me, I will write. Two times 3 minus plus. Why plus? Why not minus? By definition, that's correct. So definition was summation, right? Once you define something, you stick to it. That's the structure. It's not arbitrary, we just change it. Right? You could change the definition, that will be something else. You're free to change the definition and maybe you can get people to like it if you try hard. But that's the definition everybody, for now, is operating based on. So it's a plus. Now, of course, it ends up being negative, right? Because one of them is negative. But it would be misleading to write it minus. Okay? I'm going to write the next line. What's the next element? -1 times -1 plus 11. So it's not that mentally taxing to just track it. Obviously, it's not fun to do it if the vectors are very long, because we might make a mistake adding them up. But that's just how it goes. And then we have 6 plus minus 15 plus 1 minus 22. I'm not going to try to add them up because this is being recorded. I refer to my next slide, and the answer is minus 30. So that's a very basic operation that we're going to use to build on it as from here. Jesse says, wise professor. He's been there, I'm assuming. Usually things don't work. You try to solve something in class. From experience, usually it doesn't work out. As soon as you leave the class, it works. All right, so you could use whatever notation you like. Summation is very compact. Writing in a vector or matrices is more visually aiding, but it's non-compact. I actually like this one myself when I'm not necessarily writing the vector, but just writing the letters. In physics literature, they love writing summation, but it gets very complicated if you have really, really crazy terms for modeling the universe. It gets really difficult to track. Whereas if you write it in a matrix, I find it more convenient to track. But in any way, you can choose your style. We are not telling you what to do here. Let's try it in Julia, A times B. Well, luckily enough, this is defined, right? So in a computer, it's not that computer understands what is the asterisk. It can mean many different things if your objects are of different types. If it's a vector, if it's a matrix, maybe you're working with characters. In fact, you can define that operators for any type of object in your program. A lot of programs allow you to define that operation. But Julia, similar to MATLAB, the point is being comfortable doing matrix manipulation. So this means, by default, this means standard matrix multiplication or vector multiplication. Now we do that and we get the same answer. It's an array of one element. The type is float 64. It's a floating point number because we have dot 0, so it could be other numbers after that. So there's a question, Emerald is asking why is the answer a float and not an integer? It's a good question because it could be integer. I think it would be integer if A and B were defined as integers. Now it is probably because I put dot here. I'm forcing the program to define it as float. If you don't put dot, I think it will end up being integer. Now I'm not doing it for every element in the vector. So we also learned that if one of the entries of the vector matrix is float, that overwrites every other element. Then all of it must be float. So it's because of this dot. You try removing that dot, see what you get. You should get integer. These are headaches that you don't have on the paper. In the computer, you have to deal with more stuff like types of your numbers. Okay, so now let's talk about partitioning rows and columns of a matrix. So now, suppose I have a matrix A. It has 2 rows, 3 columns. This is a 2 by 3 matrix. You can read this 2 by 3. We don't usually say 2 times 3 matrix. We say 2 by 3 matrix. How would you go about partitioning this matrix? Make an obvious guess. Your first attempt.
What do you mean by partition?
Partitioning means dividing this matrix into smaller units, right? In a
By row?
Let's do it by row first, right? If I have a square, I can partition it into 4 smaller squares, right? That's what I mean. Is this okay if I say this is one row and this is another row? Right? Sounds like it makes sense to all of you. Can I do this? I can't? Why? You can't just say you can't. That doesn't feel great. A reason would be highly appreciated too. I just made this up, right? You're stopping me. You can't do that. That doesn't make sense. And you're right. But can we articulate a reason? Yeah, yeah, they're not the same size in the sense that we wanted to partition them in rows, right? We can't have 2 rows in 1 row. That becomes inconsistent with what we have built so far. 1 row consists of all the columns of that matrix. So it must be from the beginning to the end. All right, so we're not going to think about it, chopping them into pieces halfway through. It's just 1 row, first row, second row, third row, and so on. How about columns? Just do it, right? In the obvious way, we can also do this. And for the same reason, we don't try to chop it halfway through, because a column must contain all the rows, right? All right, so it sounds like you're comfortable with what will come up already. You can guess how it should be. So a partition of A, matrix A, into rows is nothing just defining each row as a row, each row of the matrix as a row vector, and stacking them like this. Row 1, row 2. And we could write them as separate row vectors. Why we have 2 rows? Because the matrix was 2 by 3. By definition, it's 2 rows, 3 columns. It's not a matter of guessing. We will know that we will also have 3 columns. So when we partition in rows, obviously a row vector has 1 row and several columns. So each vector here will be 1 by 3. 3 is the number of columns of the matrix, right? And 1 is because it's a row. It's a vector. Now let's try this for columns. As we expected we will get 3 columns. 1, 2, 3. Now what's the size of the column? One by 2. Try again. 2 by 1. So in principle, you store the same information, but we're going to be in trouble if we want to multiply 2 row vectors. 2 by 1. 2 rows, 1 column. So again, the number, because it's a column vector, we partition the matrix into columns. It has the same number of rows as the matrix itself. And because it's a vector by definition, it's 2 by 1. Similarly, we can write them as just independent vectors. And that's called a partition of A into columns. It has the same number of rows as the matrix and 1 column. Now, why do we talk about this? Because we want to generalize it. We talk about a specific case and make sure we understand the syntax. Now we want to write down the general form. Now, you should be able to follow this visually, and if not, feel free to ask a question. I'll explain it using the general notation. So what are we doing here? We have an n by m matrix. N rows, m columns. How many row vectors I can get out of this matrix? N. That's correct. How many columns? Did you say N? M. They can't hear you, so I can change your answer. No, everybody said M. I was the one changing their answer. So you can already see it here, 1, 2, all the way to row n. And if we partition it in columns, this should give us m column vectors. What's the size of each row vector? N. 1 by n. So it's, if you say m, it doesn't tell me if it's a row vector or a column vector. Now later when you guys are talking with your friends, that's okay, you can say m. But during a lecture, you need to specify rows and columns. Because if you get the length of the vector is m, but this could be also a column vector, right? So it leaves me wondering which one you were referring to. So we have 1 by m. So we have 1 by m row vectors. Now let's use a dummy variable again. I use I. I want to show the ith row, which is an 1 by m row vector using a general notation. And I can vary from 1 to n. So by looking at these rows here, we can see that the second index, because we partition in row, the second index is fixed. For every row, the second index is just 1, 2, 3, up to m. It's not changing. But the row index is changing because the first one is 1. It's constant because we are in the first row. The second one is 2. And the last one is n. So I can fix the indices of, for each row vector, I can fix the indices of columns and use I to point out an arbitrary row in the matrix. And I can be any number from 1 to n. Obviously cannot be 1.5. We are talking about whole numbers. Let's do the same thing for columns of our matrix. We partition A into columns. What's the size of each column this time? N by 1. That's correct. How many of them? So we have m n by 1 columns. Now, by the way, when you look at this matrix, what's the size I should put here? I think that's a good test. Given all the information from the notation you see, if I see the right-hand side and nothing else, based on previous definition that are the same as what you see here, how do you read this line? By this line, I mean, how about you make out of this? Is it a scalar? Is it an array of bicycles with different colors? Is it? It's a row vector, right? That's a trick question. Don't answer. It's a row vector of? 1 by n. Does it make sense? 1 by n. But we have m columns. Oh, you're saying it's 1 by m. Well, that seems to be what we guessed, but what to make out of this equality sign here, that the left-hand side is a matrix. Clearly, the two sides of the equality must be the same, because this side is n by m. How can we explain this?
N column vectors of 1 by m elements.
It's m column vectors of n by 1 vectors. Right, so you can say 1 by m, but that's incomplete because it's a 1 by m arrangement. It's not a vector really. 1 by m array of n by n vectors. So because this is 1 by m, but each of these columns, this is 1 n, this is n by 1, n by 1. So this is the same as arranging these each column next to each other. So this is actually 1 by m array of n by 1 vectors. So it is indeed n by m. This could be a compact notation somebody is using. You read it, you think, oh, that's a row vector, but this is not a scalar, this is a column vector. So it makes it a matrix, actually. Could be confusing, but that's the meaning. If it's clearly specified that each entry is a vector, this turns the notation into a matrix. But we won't make things intentionally complicated. I'm just playing with indices for practicing. So we used I to point out the arbitrary row of our matrix. How about we use J to define an arbitrary column? Similar to the last case, this time, because we partitioned the matrix into columns, the row index is fixed. It's always 1, 2, 3, up to n. 1, 2, 3, up to n. And that's true for all columns of our matrix here. However, the columns are changing. This is 1, this is 2, and you see 2 is fixed. This is m. So I can replace the jth column notation using this. We have 1j, 2j, nj, and j can vary from 1 to m, number of columns. And that will be jth column of my matrix, and it's n by 1 vector. Does this make sense to everybody? Don't let the notation questions get accumulated. Be quick in asking them. Because they can become deadly. If you have a few notation questions at the same time at some point, it makes it impossible, as if you're reading a foreign language. It doesn't make any sense anymore. Okay, so hopefully this is a simple way to reference rows and columns of our matrix. And I think now we're ready to define the standard matrix multiplication. Suppose we have a matrix A, and A has n rows and k columns. Now suppose we have another matrix B. B has k columns and m rows. And the values of n, m, and k can be any integer greater than or equal to 1. If it's 1, it will turn the matrix into a vector. But in general, they can be bigger than 1. Now, the standard matrix multiplication, it works like this. I have an n by k matrix. I want to multiply it by a k by m matrix. This will give me a new matrix. That is n by m. What is going on? Let's understand the definition. It sounds like the first matrix must have the same number of columns as number of rows of the second matrix, right? K columns, K rows. And then as we sum somehow over, as we multiply these two matrices somehow, it seems like K will disappear. And then we are left with the number of rows of the first matrix and the number of columns of the second matrix, and that will be the size of the results of multiplication, n by m. So this is the definition of the product of A and B. The standard way is saying that it involves multiplying rows of A by columns of B. So we know already how to multiply a row vector by a column vector. We just saw it today. We could multiply a row vector by a column vector, right? But what was the condition on the definition of multiplying a row vector by a column vector?
It was n by 1 multiplied by 1 by n.
I'm referring to here. Maybe repeat. What do you got?
They need the same number of elements.
Right. We need the same number of elements, right? It was trivial, but the definition wanted us to have the same number of elements, and we called it K. And we talked about it that otherwise we can't do it. We don't know how to do it. It's not defined. Now, the matrix multiplication is telling us that the standard way of doing matrix multiplication, A times B, involves multiplying rows of A with columns of B. Now, if that's the case, they better have the A must have the same number of elements in its columns, right? Because the columns of A tells us how many entries we have in each row. Must have the same number of columns as rows of B, because rows of B will tell us how many entries we have in each column of B. So it follows directly from the previous definition that they must have the same number of columns and rows, respectively. Okay? We're not making up a new thing. It is consistent with the previous definition. We will, of course, see examples and we'll look into it. Otherwise, it's not very helpful to just look at this definition. So we had this question, if matrix multiplication is commutative. And the answer was it's not. Now you might ask, what does it mean to matrix or object commute? A and B, we say A and B commute if you can swap the order. Right? If A times B is the same as B times A, we say they commute. You can change the order. Now with numbers, you can do that, right? 2 times 3 is the same as 3 times 2. No problem. So real numbers that we work with, they commute. We don't think about it because then we don't care about the order of multiplication. But when you work with matrices, this is not true. For two reasons. One is because of the syntax, the other one is because of the semantics. What's the syntax error? Now, same definition I have here, A times B, right? This is A, B. What happens if I write it BA?
Aren't necessarily the same. You have this number of columns and rows between the matrices.
Right, the disaster would be that B is K by M, A is K by N. I mean, K, it's like multiplying a vector inside this algorithm. We already know that we end up multiplying two vectors. One has M columns, the other one has K rows. That's just not defined. So this is syntax error. By definition, it's wrong. We can't do it. We'll see a case that if your matrices are square, same size, it is perfectly fine to do it, but it's very misleading because semantically it's not correct. You just don't get the same answer. You're not going to get an error if you do it in a program. You just don't get the expected answer. So it's semantically wrong. And just to write it, don't commute. And generally, things get interesting when multiplication is not non-commutative. If it's commutative, mathematicians especially, they get bored easily. But we use matrices for a lot of things in engineering, and they don't commute, so the order is very important. First example, we're going to keep it easy. We keep one of them to be a vector. So the first matrix is a 2 by 2. And the second one is 2 by 1. So I can write B times A, right? Can I do that? Because B is 2 by 1 and A is 2 by 2, and we can only multiply if they don't have the same number of columns and rows. No? That's completely, I negated everything we learned so far. So I can't do this because they don't have the same, B doesn't have the same number of columns as the rows of A, but I can write A times B. 2 by 2, 2 by 1. What do you expect to be the answer? Let's call it C.
It'll be a 2 by 2.
2 by,
Oh, wait, sorry, no, 2 by 1.
2 by 1. Yeah, because whatever is in the middle, you just drop it. I think about it as, we'll see, we'll be summing over that number. It's the common number between two matrices, and it will disappear. So now from the syntax we learned so far, that's what we expect to get. Of course, we don't know, now C will be, let's call it C1, C2, but of course we don't know the numbers, but we expect to see something like this. Okay, so the definition told us what you should do. You should multiply each row of A by columns of B. Now, the way it works that for every row, we should multiply that to every column of B. So row 1 multiplied by column 1, column 2, column 3, right? All the way to the end. The second row, do the same thing. Here we only have one column, so first row times first column. This is a row, this is the product of a row vector by a column vector, right? It's not just scalar multiplication. So first row by the first column, the second row of A, again by the first column of B. We do not have more columns of B. Now we calculate each row. It should give us one number. That was the result of multiplying a row vector by a column vector. The first one will give us 17, and the second one 39. So that is the expected 2 by 1 matrix. Because we can also write it down. So the first row of A, we partitioned A into rows. The first partition is 1, 2, right? Remember, A was 1, 2, 3, 4. And the second one is 3 and 4. We partition B into columns, but it only has one column. It's a vector already. So we have B1, A1, A2. So we get 1 times 5 plus 2 times 6, that's 17. We have 3 times 5 plus 4 times 6. Apparently that's 39. And let's try this in Julia. So the same asterisk operator that we used for vector matrix, vector product, it's actually matrix product. Because vector multiplication, if their dimensions make sense, it's the special case of matrix multiplication. So it is, or you could say matrix multiplication is built on vector multiplication as a basic operation. So they use the same operator. Okay, so we multiply A by B, and we get the 2-element column vector as expected. Why are we getting integer this time? That's correct, because I am using integer. I'm not putting dot anywhere to tell the computer this is a float number. In MATLAB, if you're familiar with it, I think this will be by default float. It's called double, but it means float. Float can have single precision, double precision. Double, the number of digits you keep after the dot is twice of the single. Let's say one is 7, the other one is 15. One is 16, the other one is 32. So it's integer because everything is defined as integer. All right, so now I told you that's a syntax error if you multiply B by A. But you have no reason to believe me until you see the code, see the error, and that will be the definite answer for us. And if something doesn't work at any time, we blame the computer, not me. That's the benefit of proving things this way. Let's see, can we do this? We talked about it, we can't because B is 2 by 1. A is 2 by 2. The number of columns of the first one, B, does not match the number of rows of the second one. Therefore, this is not defined. Because you will simply get stuck here when you are trying to do this operation. They just don't have the same size here, right? It's just not possible. Should we try it in Julia? Do not try this at home. If you are watching this, you will get a syntax error. So the computer knows actually, it tells you that it will give you a very specific message that the dimension does not match. Right? So before going into the operation, the program will check that if the dimension makes sense. It obviously doesn't make sense to start the operation and then halfway through you're realizing and then issue the error. That's too late. So typically these methods check the inputs to make sure things are correct, and then they will carry out the operation. And that's a very good way to write programs. You first verify your inputs, make sure they're correct, and then do whatever you want to do and give the output. And that's what's happening inside Julia when you type B times A. Dimension mismatch. Let's make it a little tricky. Now, both of them are 2 by 2. We are about to check whether A times B equals B times A. Now, if this is true, it should be true for any B and A. Right? When you claim that A times B is true equals B times A, if you find one example that that's not true, then it's not true in general. That's enough to basically reject the hypothesis. But on the other hand, if it's true, you should prove that it's true always. That's how it works in math. You can't just say, I tried it 10 times, it worked. Sounds like we have a general rule here. No, that's not how it works. You should show that it works all the time. All right, so what should we do? A times B. Partition A, the first one in 2 rows. Partition B, the second one in 2 columns. Now, when we write it in the partitioned form, I'm going to call this R1, R2, C1, C2. Row 1, row 2, column 1, column 2. So what we see here actually is R1, C1, R1, C2. All right. Multiply the first row by the first column. We get 1 times 5, 1 times 5, plus 2 times 6. That will give us the first number here. Now we go to the second column. 1 times minus 2, 2 times 1. We add them up, we get 0. We go to the, we're done with the columns, right? Now we go to the next row. 3 times 5 plus 4 times 6. We get 39. Now, how do we know 39 should be here? Why not here? Is it automatically tracked? Or is something that we should be careful about it? Can you please repeat? Right, so you're saying that it's the second row multiplied by the first column, right? That's why it's in the first column. So it is in the indices of the rows and columns. It is the second row of the first matrix and the first column of the second matrix. So it's 2 and 1. Right? So it is tracked automatically, actually. So as we operate this, we sum over the common index, which is the number of columns of the first one, and the rows of the second matrix. What's left is the row index of the first matrix and the column index of the second one. So we do the last one too. It's R2C2. Obviously, the index is 2 and 2. It becomes negative 2. Zoom is suspiciously quiet. There's no question. Are you still with us? Yes. Okay. Now, so it makes sense to do A times B. Both are square matrices, 2 by 2. What about B times A? We can do it, right? Because both are 2 by 2. So we can do it. You repeat the exact same operation, but it turns out the result is different. It's not the same. See, the previous numbers are very different from what we got here. Because multiplying each row of A by column of B, right? It's not the same thing as rows of B times columns of A. It's just they're different numbers when we repeat that operation. So we can't expect to get the same result. That's the basic reason why. Because by doing it the other way around, B times A, we simply have different numbers here for row and column. So it's not going to be the same. And that's not true in general. It will be a very, very special case if you see that's true. So let's try. Define A and B, A times B, B times A. We see again in Julia. That's the same answer we got with hand calculation. I think I'm not checking it, but I think you can check to see 2 equality signs, right? Check if they're equal. Now, to be equal, each of the corresponding entries of the matrices must be the same. Entry 1, 1, 1, 2, 1, 3, right? And so on. Okay, so the general form of what's going on in Julia is that we get A is n by k. Partition A into rows. We have B is K by M, partition B into columns. And as we discussed, the standard matrix multiplication involves multiplying each row of the first matrix by the columns of the second matrix. So each row by the column, row 1 multiplied by every single column of B, row 2 multiplied by every single column of B, and so on, right? We could use our summation notation as well and bring in the dummy index that we have. This makes it very compact. So for each entry of the result of multiplying A times B, we can exactly calculate that number by just calculating this summation, which is go over nth row of A and columns of mth columns of B, right? And multiply corresponding indices as a row vector, column vector multiplication and sum them up. So there's going to be a lot of multiplication and operation, but that can be done very fast. Now, is it necessary? The important question is that, is it necessary to calculate these terms one by one? Do I need to calculate this part to move to this part, and then the next one, and then the next one? I don't, right? I can just make more copies of rows of A and do all of these at the same time. So it sounds like it's possible to calculate every single number here in parallel. That's a very promising thing to see, because not something we talk about it, but usually these operations are very optimized in languages like MATLAB and Julia to do calculations in parallel using whatever number of cores or threads you have on CPU. By default, it's not on GPU. And for very, very large scale operation, obviously not something like machine learning and deep learning, they do it on GPU. Because they don't want 20 cores, they want 1,000 cores to do some calculations in parallel. Now, it's not a topic of this class, but it's related to the computational view of dealing with these equations. Parallel computing is also possible here. And you can build large matrices. Once you learned how to do for loops and do calculations, build 2 large matrices and multiply them directly using Julia. Then write a loop, a for loop, and calculate each entry in a sequential way. Loop over the first one. In the loop, you calculate the first one, then second one, third one, and fill in your matrix. Now, you should get the same result and then time it. In Julia, you can also time. I think 3B can teach you. I don't remember the command. In MATLAB, it's tick-tock. You tick, start recording, and then talk. You end the timing. I will tell you the elapsed time. How long did it take to go from that line that you put tick until the line that you added talk? So you can time it and see how long does it take for Julia to run that one line, and how long does it take for a for loop to do it. But I think the matrices should be large. Don't try 2 by 2. Try 1,000 by 1,000. Or 10,000 by 10,000. So the last topic of today is about the matrix view of swapping rows. Now suppose I'm given these equations, this set of equations, and if I write this in matrix form, which by the way, now you can calculate it. You can multiply this matrix by vector x1, x2, and x3, right? That should generate this set of equations for you. Because this is 3 by 3, this is 3 by 1, the result will be this 3 by 1 vector. Now, this doesn't have any interesting structure. It's not lower triangular, it's not upper triangular, it's just a regular matrix. But if I just swap these two rows, what happens? Becomes a lower triangular matrix. Now that's a big difference because it wasn't anything special. We couldn't solve it. As soon as it becomes lower triangular, we can do, what can we do? Forward substitution, right? From last time we know how to do forward substitution and we can solve it. So that's a big difference. And it's as simple as just swapping rows. So let's write down the matrix form of both that unfortunately ordered equations and this nicely rearranged system of equations. Let's call this the original one. The other one is the lower triangular one. You could use different notations. It doesn't matter. So this one is lower triangular. This one is not, because not all entries above the diagonal are zeros. Now the question is, of course, how can we convert A subscript O into A subscript L using matrix multiplication? Somehow manipulating these matrices, we can get one from the other one. Same thing for the right-hand side. That should be equivalent of we seeing the equations and then swapping the rows manually, right? But that sounds like very complicated for computer the way we do it. We're just looking at it knowing that we should do that. And that's the topic of permutation. Trivi is pointing out that TikTok actually works in Julia too. That's interesting. So you can time your code with TikTok. You can check the chat and Zoom. I'm sure you'll do examples on that. So permutation matrix will allow us to do that. Now I'm going to claim that swapping rows can be accomplished with this matrix. This strange arrangement of zeros and ones. You have 1, 1, 1. The claim is that this will do the job. If I multiply P A subscript O, that will give me a lower triangular form. Now, of course, we should also multiply with the right-hand side, B, right? Otherwise, if you have a scale right? You have one weight here, one weight here. When you multiply, it's like you add a weight this side, but not adding it to the other side. Obviously, you're ruining the balance. You should always multiply both sides of the equation by the same element. Let's check the claim. Sounds like it's working. We multiply P. We do all of that, partition in rows, in columns, or just use Julia for the sake of this example, and you will get a lower triangular matrix. Do the same thing with B, and what happens, these two numbers are swapped. The question is, how this happened? Now, P is called a permutation matrix. These are a very important group of matrices used for reordering, permuting, and rearranging rows of matrices. You can verify this in Julia. You get the same answer by defining all the terms. And the key is that a permutation matrix can be constructed from the identity matrix. Now, if you are familiar with the identity matrix is a matrix that has ones on its diagonals and zeros everywhere. So this is, for example, a 2 by 2 identity matrix. You can say I2. Or a 3 by 3 identity matrix. Now, it sounds like the general rule is that we start from the identity matrix, we swap the rows of the identity matrix for the operation we want to do, and that gives us the permutation matrix we want. For example, I want to convert 1, 2, 3, 4, 5 to 1, 2, 5, 4, 3 by swapping 3 and 5, row 3 and row 5. What I do is that I take an identity matrix of size 5 because my vector is 5 by 1, and I swap the third and fifth row of that matrix. That will give me P, my permutation matrix. Okay? So I did nothing special. Just swap these two rows. Then I define V, 1, 2, 3, 4, 5, and P. Then permute V by P multiplied by V. This is 5 here now and 3. So in general, this works. You start from the identity matrix. You can construct your permutation matrix like this. Now, it is a good example to look into it why this happens. If you follow the matrix multiplication, the logic should appear clear after going through it, because this 0 and 1s is just picking a particular element, right, when you multiply. So going through that, it will be very interesting to reach that realization. And maybe post on Piazza if you have any questions.
So just in general, is it always going to be, the identity matrix is always going to be the same amount of, or it'll just be like an n by n of the same amount of rows that in your swap is?
Yeah, the question is in general, it must be the same number of rows.
Yeah. Because like, this is like a 5 by 1 matrix, or like I guess you could call it a column vector, and then the identity matrix is 5 by 5. But like if you had something that was a 5 by 3 matrix, and you wanted to swap rows 2 and 3 or whatever, you would still have a 5 by 5 identity matrix that you would swap.
Yeah, the question is, does this work on matrices, not just vectors, right?
Yeah, well, I mean, I know it does
Yeah.
I was just curious as to like how to determine how big the identity matrix is supposed to be.
Okay, so let me finish the class, then we talk, okay? Because this is the end of the recording. People watching this later, they won't see probably from here. So next time we'll talk about LU factorization. There's a trick. There's a second way of doing matrix multiplication. That's in chapter 4, but I'm going to talk about it next time. But you might have read that already. So next time we will talk about how to factorize a matrix into a lower and upper triangular matrix. And see you on Wednesday.